Stairway to Graduation is a robot, built by Koc-University mechanical engineering students as their final year project in the Mech 491 course. The team members are Aran Kanal, Manmet Dogukan Weissel, and Kon Karaman. The task of the robot is to climb 3 steps with heights of 10, 20, and 30 centimeters respectively. The robot should climb the stairs without losing balance. The success of the robot is evaluated based on ability to climb the steps, size, the smaller the better, speed, and payload capacity. One of the key mechanical parts of the project is the DC motor to shaft adapter, which connects the D-type output of the DC motor to a custom plus-shaped shaft. This adapter ensures precise torque transfer and minimizes misalignment, which is essential for the robot's smooth and reliable performance during stair climbing. Another crucial component is the LiPo battery mount, designed to securely attach the battery to the chassis. This mount was custom built to match the dimensions of the battery, providing a snug fit that prevents movement during operation, even under vibrations or sudden shifts. In addition, we designed and 3D printed a motor mount specifically tailored to hold a DC motor with an outer diameter of 25 mm. The mount was printed using ABS filament, chosen for its high strength and thermal resistance, ensuring durability under operational stresses. To achieve a precise fit, we incorporated a small tolerance of 0.2 mm into the design. This allowed the motor to fit securely within the mount without requiring excessive force during installation, ensuring both stability and ease of assembly. We also produced custom mounts for other key components, such as the Arduino Uno, front and rear axle motors, breakover motor, and L298N motor driver. Each mount was specifically designed and 3D printed to fit its respective component, providing stability and optimizing the overall layout within the chassis. These 3D printed parts were critical in ensuring the mechanical integrity and functionality of the robot. The parts that were readily purchased are Arduino Uno or 4 Wi-Fi, L298N dual H-bridge motor driver, Power Extra 11.1 V20C LiPo battery, ESP32S, 112V 16 RPM DC motor, 212V 26 RPM DC motors. We began with the Arduino Uno or 4 Wi-Fi, which serves as the brain of the robot. This microcontroller board was selected for its versatility and built-in Wi-Fi capability, which allows seamless integration with wireless control systems. Its processing power and wide range of input-output pins make it an excellent choice for interfacing with sensors, motors, and other electronic components. By using the R4 model, we also ensured compatibility with a variety of Arduino libraries, streamlining the programming process and reducing development time. Next, we incorporated the L298N dual H-bridge motor driver. This component is crucial for controlling the rotational direction and speed of the robot's DC motors. The L298N allows us to independently control up to 2 motors, making it ideal for managing the front and rear wheel motors in our robot. Its ability to handle high currents and provide precise PWM, pulse width modulation, signals gives us fine control over motor operation, ensuring smooth and coordinated movement. For power, we chose the Power Extra 11.1 V20C LiPo battery, which supplies the energy needed to drive the motors and other electronic components. This lithium polymer battery was selected for its high energy density and lightweight design, 2 key factors in maintaining the robot's compactness and mobility. The 20C discharge rate ensures that the battery can deliver the high currents required by the motors during stair climbing without significant voltage drops, which could impact performance. In addition to these control and power components, we utilized an ESP32S microcontroller module. This module was integrated into the system to enhance wireless communication capabilities. Its dual-core processor and built-in Wi-Fi and Bluetooth functionality enable real-time data transfer, remote monitoring, and the potential for future scalability. For example, the ESP32S allows us to transmit sensor data to a smartphone or laptop, providing valuable insights into the robot's performance during testing. Finally, we come to the motors, the driving force behind the robot's movements. We purchased one 12V 16 RPM DC motor for the breakover mechanism. This motor was selected for its low speed and high torque characteristics, which are essential for smoothly lifting the robot's segments over steps of varying heights. Additionally, we used two 12V 26 RPM DC motors for the front and rear axles. These motors offer a balance between speed and torque, enabling efficient forward motion and stability during stair climbing. The higher RPM of these motors ensures that the robot maintains a reasonable speed while still providing sufficient power to handle the weight of the chassis and payload. In the modeling phase of our project, we analyzed the relative rotational speeds of the 3 DC motors that power the robot. This was crucial for ensuring precise stair climbing and maintaining balance. We simplified the robot's mechanics by representing its geometry as an isosceles triangle during stair interaction. The base corresponds to the wheels on the ground, and the vertex represents the breakover joint that transitions the robot over steps. The angular velocity of the breakover angle, denoted as theta, controls the lifting motion, while the angular velocity of the wheels, omega, drives forward movement. Assuming the wheels roll without slipping allowed us to establish a direct relationship between these velocities, simplifying the model. Simulations in MATLAB and Python validated the model, helping us fine-tune the ratios of theta to omega for optimal performance. This ensured synchronized lifting and propulsion, stability, and efficient motion for climbing steps of 10, 20, and 30 centimeters. In conclusion, the project successfully demonstrated the robot's ability to climb stairs of varying heights while maintaining balance and meeting performance criteria such as size, speed, and payload capacity. Future work could focus on enhancing the robot's adaptability to irregular stair geometries and improving energy efficiency for longer operational use.